All right, now let's state and prove a formula for the binomial coefficients and choose k. So recall n choose k equals the coefficient of x to the k in 1 plus x to the nth. 1 plus x is a binomial, that's why this is called a binomial coefficient. It's also equal to the number of k element subsets of an n element set, like 1 through n. This is also equal to the number of binary words a1 through an having k1s. Now I claim that n choose k, the formula is n factorial over k factorial divided also by n minus k factorial. And I'll do the proof in a minute, but I want to play with this a little bit. So first of all, let's observe that by this formula n choose k and n choose n minus k have to be the same, because the first one is n factorial over k factorial n minus k factorial, and the second one is n factorial over n minus k factorial n minus k factorial. Which is n factorial over n minus k factorial. N minus the quantity n minus k is, well, n minus n is 0. Minus k is positive k. So that gives us k factorial. So we can see these expressions are exactly the same thing. Another way to see this is that n choose k we could think of as the number of ways to take k objects out of a box that has n objects in it. So we've got n objects, take k out. N choose n minus k could be the number of ways to start with a box of n objects and choose n minus k to stay in the box and take the other k out. So in that sense, obviously they're going to be the same thing. Alright, now before we prove this, let's compute a couple of these. Let's compute it for n equals 4 and all different values of k. Well, k from 0 to 4, because if we're going to choose a subset of numbers 1 through 4, it'll have at least 0 elements and at most 4 elements. So if k is 0, there's only one 0 element subset of 1 through 4. So the number of these is 1. K is 1. The 1 element subsets are 1, 2, 3, and 4. So there's 4 of those. The 2 element subsets are 1, 2, 1, 3, 1, 4. Again, I'm leaving out curly braces and commas just to keep this nice and neat. 2, 3, 2, 4, and 3, 4. So there's 6 of those. The 3 element subsets are 1, 2, 3, 1, 2, 4, 1, 3, 4, and 2, 3, 4. There's 4 of those. And then there's only one 4 element subset. We take all of the elements, 1, 2, 3, 4. So there's one of those. All right, now let's plug in these numbers and see if n choose k actually is the right number in all these cases. Now since n choose k and n choose n minus k are the same, we can see that symmetry here in the number. We've got 1 and 1, 4 and 4. So we can compare two of these ones. So 4 choose 0. And 4 choose 4 should be the same. And they are 4 factorial over 0 factorial 4 factorial, which is 1 because 0 factorial is 1. That's good. We got 1 and 1. Then 4 choose 1 and 4 choose 3 should be the same. They're both 4 factorial over 1 factorial 3 factorial. And of course it doesn't matter whether you write the 3 factorial or the 1 factorial first in the denominator. So that's 4 times 3 times 2 times 1 over 3 times 2 times 1, which is 4. That's good. We got 4 and 4. And then if we look at 4 choose 2, that's 4 factorial over 2 factorial 2 factorial, which is 4 times 3 times 2 times 1 over 2 times 2. 2 times 2 is 4, so we'll cancel that. We get 3 times 2 times 1, which is 6, which is good. That matches the number of 2 element subsets of 1, 2, 3, 4 that we have. All right, let me rewrite the claim. Claim that n choose k equals n factorial over k factorial n minus k factorial. I want to prove this two ways. So proof 1. We can get a k element subset. So first of all, these two proofs correspond to thinking of n choose k as the number of k element subsets, or thinking of n choose k as the number of binary words having k ones. So first of all, I'm going to think of n choose k being the number of k element subsets of 1 through n. Then we get a k element subset of 1 through n. By taking a k letter repetition free word in 1 through n, that is choosing letters from this set with no repetition, and by ignoring the order of the words, ignoring the order of the letters. So 2176 is going to give us the set 1, 2, 6, 7. So there are n factorial over n minus k factorial ways to do this. That is, n factorial over n minus k factorial ways to make the repetition-free word. Because we've got k letters here, and we've got n choices, and then n minus 1 choices, and n minus 2 choices, etc. And then finally n minus k plus 1 choices. multiply these together, that's n factorial divided by n minus k factorial. Of course, any of the k factorial permutations of these k letters are going to give us the same set in the end. So now we divide by k factorial to correct for overcounting. Because any of the k factorial permutations of this word give the same subset. So n factorial over n minus k factorial divide by k factorial again, and we get precisely this formula here. All right, now let's do proof number 2 using binary words instead of subsets. N choose k equals the number of binary words so A1 through AN having k ones. So that means that n choose k equals, another way of saying this is the number of rearrangements of the word that has k ones and n minus k zeros. And by the word rearrangement, formula, this is n factorial ways to rearrange n letters, but there's k factorial permutations of the one that don't make a difference. So we divide by that overcounting factor. And there's n minus k factorial permutations of the zeros that don't make a difference. So we divide by that overcounting factor as well. And there we have it. Again, we've got exactly the formula that we claimed. N choose k equals n factorial over k factorial n minus k factorial. The end.